Okay, so this part is optional, but I was thinking to provide the proof of the main property that we use in the convolution section. So why the convolution is defined the way it is, and how come that leads to this property that we emphasize in this section, the fact that we can distribute the Laplace operator over a convolution. So it's a nice application of calculus 3, calculus 2 as well. I mean, so it's a nice application of integration. And I'd like to go over it if you're curious about it, because again, even most people, if they don't need the proof, they don't care too much about it. But I think it's still important often to at least have an understanding why these definitions look like that. I mean, like why the convolution is just this particular type of integral. Why is it t minus u here? So on and so forth. So I think this proof, gives you a partial answer at least of why these definitions are chosen this way, because they are looking for a certain property, and therefore looking for that property leads to a specific definition, which is the most useful for the tool the mathematicians created in that case. So we want to prove this via the definition. So keep that in mind. This is the definition of the convolution, and keep also in mind the definition of the Laplace transform. So the integral from 0 to infinity, a function of t e to the minus st dt. So if I want to prove this equality via these definitions, let's start with the left side. So we're going to start with Laplace of the convolution, which according to the definition of the Laplace transform, this is the integral from 0 to infinity of the convolution times e to the minus st. So that convolution gives me a function of t, and then you multiply that with e to the minus st dt, and from 0 to infinity, that's the Laplace transform of this left side. So the goal is to show that this becomes the product of the Laplace transforms. So just to make it clear, this is L. Go ahead and from here. Let me actually write it down again, so it's clear which side of the equality I start from. So L of f of t convolution g of t is the integral from 0 to infinity f of t convolution g of t e to the minus st dt. Okay, so now it's time to write down what that convolution is. So we're going to insert another integral inside this integral. So f of t convolution g of t is the integral from 0 to t f of t minus u g of u du, close the inner integral e to the minus st dt. So we're going to get into calculus 3 pretty soon with a double integral, because notice at this point I can insert this e to the minus st in the innermost integral. Okay, so look carefully here. The innermost integral is in terms of u. This doesn't depend on u. So as a whole, it's like a constant in terms of u. So I can bring it inside the innermost integral. And if I do that, I end up essentially with an iteration of two integrals, right? So the integral from 0 to infinity, the integral from 0 to t, f of t minus u, g of u, e to the minus st, and then du dt. So at this point, if you didn't take calculus 3, it might be a little bit harder for you to follow, but it's not impossible. Don't be discouraged. I mean, this is essentially a double integral, but you can just think of it as an integral of an integral, and that should be fine. So for the most part, I mean, we're going to do a switch of order of integration, which it's learned in calculus 3, but again, I don't think it's hard to understand even if you took on a calculus 2 and you follow carefully the computation. So let's see this as an integral of a function of two variables in u and t, basically, in which we have a domain of integration given by a domain in the plane. So we look at not by u and t separately, but by what they describe given these bounds in the plane labeled by the axis u and t. So if I look carefully at the bounds of integration, notice the outermost bound, which is t, is between t 0 and infinity, and the bounds for u are in terms of t. So actually the order of integration matters if you think about it, right? Because for any t which varies between 0 and infinity, u varies between 0 and t. So the bounds of u depend on t, at least the upper bound of u. So with that in mind, let's actually picture the domain of integration as a double integral here. And so let's put the t, doesn't matter actually which one is horizontal or vertical, but let's put the t on the horizontal line as we normally do. And notice that this is essentially the domain of integration. If you look at this area, let's see if I can do it so that I don't make too much of a mess. Right, but that's essentially the area of the domain of integration. Okay, because again, t is between t is between 0 and infinity. Let's put actually here infinity. So this is t. There is between 0 and infinity, and for a given t, take a look at this. The u, let's put u here. So for a given t. For a given value of t, the bounds of u vary between 0 and t. So the point on this line is u equals t. Right? So the equation of that line is u equals t. Okay, so for a given t, the bounds of u are from 0 to t. But then because t goes to infinity, the domain of integration is this entire, it's this entire region below the line. And also keep in mind, we are under the assumption that the Laplace transforms for individually f and t separately, they exist and they're finite. Okay, so that's the main assumption. So we know the L of f of t exists, we know L of g of t exists, we just want to prove this property, this over here. Okay, so at this point we're going to do what in calculus 3 we learned to do in a double integral. We're going to switch the order of integration. So I'm going to do the outermost integral in terms of u, and then the innermost integral in terms of t. If you didn't take calculus 3, you may think that it's just a matter of switching these integrals. But in fact, if you do change the order of integration, the bounds will change as well. Okay, so look carefully here. If I start by integrating with respect to u first, so I mean if the outermost integral is in terms of u, clearly u varies between 0 and infinity, because this area goes indefinitely upward like that. So the bounds of u, if I start describing this domain with u, go from 0 to infinity. So now, for a given u, I want to see the bounds of t at this point. Okay, for this domain. So for a given u between 0 and infinity, if you look carefully, the lower bound of u is going to be t, because again this point is on the line u equals t. Okay, so again pause if you want to, right? So u from 0 to infinity, for a given u, fix one value of u. Now t, to describe the domain, goes from t goes from u to infinity. Okay, so in other words, either you describe the domain by vertical slices or by horizontal slices. So in this case, we describe the domain by horizontal slices, right? So I mean, we pick a typical slice, which is defined by u between 0 and infinity, and then t goes from u to infinity. So the entire double integral now becomes, I said I go from with the integral of du on the outside, yes. So 0 to infinity du, that's now the outermost integral. And then the innermost integral, which is in terms of t, varies between u and infinity. Okay, so the same function is integrated, obviously, right? So f of t minus u, g of u, and e to the minus st dt. Okay, so all we did, we changed the order of integration at this point, which of course forces us to change the bounds as well. Okay, so let's move on and notice one other important thing. At this point, because we changed the order of integration, g of u doesn't depend on t. G of u is a constant with respect to the innermost integral, which allows me to move it out of the innermost integral. It's still part of the outermost integral, but we can move it out of the innermost integral. So this now becomes the integral from 0 to infinity, g of u, and then let's emphasize the innermost integral from 0 to infinity, f of t minus u e to the minus st dt. We do that, and then combine with g of u du, that's the outermost integral. It may not seem what's the point of all this, but I hope after this step you will see where we go from here. Finally, let's make a change of variable, not finally, but at this step, a change of variable in the innermost integral. Just a u substitution, but you know, I'm not going to use u because now I already used this variable u, so I'm going to make a u substitution. Let's write it right underneath here. We're going to write y, the new variable, to be t minus u. So look carefully, my variable of integration is t. Think of u as a constant. I make a simple u substitution, y equals t minus u. So we have to change du dt into dy, and notice if I differentiate dy equals dt, again u is a constant at this point with respect to t, and carefully look at the new bounds. This is u, I'm sorry. The innermost integral is from u to infinity. So the new bounds of y are 0 and infinity, right? Because when t is equal to u, via this substitution, y becomes 0. Okay, so when I replace t with u minus u is 0. And of course, when t goes to infinity, infinity minus u, which is still infinity. So the bounds become 0 and infinity for for y. Okay, so we make this u substitution for the innermost integral. Okay, so then the innermost integral becomes the integral from 0 to infinity. T minus u becomes y, your new variable, f of y. And t is replaced by y plus u. Again, look carefully here. From the substitution, t is actually y plus u. So I'm going to have to replace t over here with y plus u, and dt is the same as dy. Okay, so that's the change in the innermost integral. Don't forget du for the outermost integral. Okay, one more little trick before we come closer to the conclusion. Let's distribute the minus s over this exponent. And we have f of y e to the minus sy times e to the minus su dy, and then the outermost integral with du. We're finally getting closer to the conclusion, because again, notice another important aspect here. E to the minus su, it's a constant with respect to y. This guy can be pulled out of the innermost integral at this point. So the integral becomes g of u e to the minus su, and the innermost integral is from 0 to infinity of f of y e to the minus sy dy du. Okay, so but what do we have now in the innermost integral? Take a moment and take a look, right? I mean, what we have here is precisely the definition of the Laplace transform. By the way, if it's not clear here, you could replace y with t. I mean, this y is the dummy variable, it's the variable of integration. So you could simply replace this with f of t, again, e to the minus st dt. The variable of integration doesn't matter, right? The point is, what you have here is the Laplace of f of t. F of y, Laplace of f of t. We can replace that with t. for our purposes here. So inside this integral, we have now the Laplace transform, which we know it's a finite function, it exists. And we can put it out of the outermost integral. L of f of t, we can put it out. Again, L of f of t, f of y doesn't matter. I hope it's not confusing here. I mean, I had to use y because I used before t, but just for computing the innermost integral, you could simply replace y with t just to revert back to the original notation when you took the convolution. So the fact of the matter is, the key point here is that the L of f of t comes out of the integral, and what's left is nothing but the Laplace of the other function, if you look carefully. G of u e to the minus su with u between 0 and infinity. And again, you could change that to t, right? I mean, you could change, it's the Laplace of g of u, but that's the same as Laplace of g of t, right? So I mean, whether you write g of u e to the minus su du or g of t e to the minus st dt, that's still the Laplace of g of t. I mean, the Laplace of the function is a function in S, right? I mean, if you set this, if you solve that integral, the variable of integration doesn't actually matter. So to summarize, because of the way the convolution is defined, when you take the Laplace of the convolution and you do these computations, this change of variables, you end up with this situation in which one Laplace transform becomes part of an inner integral, so it can be taken out as a constant, and what's left is the Laplace of the other. And that's why in the end, you end up with just the product of the two Laplace transforms. So I hope that's helpful to understand why the definition of the convolution is the way it is. But again, that's optional. That's not obviously part of the test or anything. Just the proof if you're curious about it. So that's it for this additional remark or video on the topic of convolutions.